So yes, I must say that most of this work it was done in Paris while I was in Paris. So, and some of the work I will talk about will relate about work of students which are in Paris. So I will say it. So what's the aim of the talk is to give a not exhaustive panorama of active direction in derived geometry. So I will first explain what derived geometry is. And the focus will be more on geometry than on topology. So what I mean by topology is derived geometry over ring spectra and so on. So both areas are very active, but I will concentrate on the geometrical side. And this is a list of people involved in the topics I will talk about. So this is the plan of the talk. I will give a very quick introduction to derived algebraic geometry. And most of the talk will be concentrated on derived symplectic and Poisson geometry. But I would like to, time permitting, I would like to give some ideas on other directions, especially derived analytic geometry, which is, and maybe EN motives, which is something quite new. Okay, so quick introduction to derived algebraic geometry. So this is the diagram that I use to explain roughly what is derived algebraic geometry. So you start with commutative algebras over K, and then we know that schemes are described as functor of points, functors from commutative algebra to sets. Then there are other kinds of, so if you want to classify objects which have automorphisms, then you have one stacks, which are functors to groupoids. And if you want to classify objects that have higher automorphisms, like perfect complexes on a scheme, you have to move to infinity stacks, which are functors from commutative algebras to simplicial sets. This diagonal arrows was introduced, defined, and studied by Carlos Simpson, infinity stacks. But this part, so the upper triangle there is not derived. It's say classical algebraic geometry, and the derived part comes when we change the source category. So we moved from commutative algebras over K to simplicial algebras over K. And we consider functor, again, to topological spaces or simplicial sets. What happens now is that both source and target, so simplicial algebras and simplicial sets, they are homotopy theories. So they are, if you want, model categories, or infinity categories if you prefer. And the construction we want to make to build derived algebraic geometry has to take this infinity or homotopical aspect into account. And this is the functor of points point of view, but there is also another approach by Lurie that uses so a scheme can be viewed as a functor, but it can be viewed also as a ring space, and what Lurie does is generalize this point of view. So a derived stack would be, in his case, an infinity topos with a structure ring spectrum on it. But basically, if you want an idea what's going on here, is that you want to glue, like for schemes, you glue commutative algebras up to isomorphism or spectra of them. Here you want to glue simplicial algebras, but not up to isomorphism. So you don't want a space with a sheaf of simplicial algebras, but you want to glue these simplicial algebras up to weak equivalences, weak homotopy equivalences. I mean, this is the image of what one wants to do, but this is not the way it's technically it's constructed. Yeah, let me add a remark that if we work over a field of characteristics, well, any Q algebra, we can replace simplicial algebras by CDGAs, which are non-positively graded differential graded algebras, with differential that increase the degree in my convention. And over Q algebra, the two theories, simplicial algebras and the two homotopy theories, simplicial algebras and CDGAs like these, are equivalent. And I will do this, so I will replace simplicial algebras by CDGAs everywhere in the symplectic and Poisson geometry part. So what we do? So first we define the derived version of the étale topology on these simplicial commutative algebras, opposite categories. So think about these being derived affine schemes. And so I say that a family A to Bi is an étale covering family if two conditions are met. So on the pi naught, the pi naught are just commutative algebras. On the pi naught is just an étale covering family of usual rings. And for higher n, sorry, the pi n, so if you look at CDGAs, the end cohomologies are just pulled back on pi naught, or h naught, if you want. So the idea is that everything is as usual on the classical parts on the pi naught, or h naught, if you want. And on the higher cohomologies, everything is as trivial as can be, so it's just a pullback. Let me also remark that this is not an ad hoc definition, so that you can define. So the way we define this is that we define using the right version of lifting property for étale maps, and we proved. So this is actually a theorem that A to Bi is étale in the sense of the lifting properties, if and only if it satisfies these conditions. So once we have this notion of topology on the derived affine schemes, then we can consider functors from, as I said in the first slides, functors from simplicial commutative algebras to simplicial sets. And I impose I make this functor in this category of functors into an homotopy theory. So if you want a model category or an infinity category, where weak equivalences are given by maps that induce isomorphism on the sheaves of pi i's for any point, base point. And once I have these weak equivalences, I can invert them, and then I get what I call d stack of k over k, which is the homotopy category of derived stacks. So with this definition, what is a derived stack? So it's a functor from simplicial commutative algebras to simplicial sets that sends weak equivalences of simplicial commutative algebras to weak equivalences of simplicial sets. And it has descent with respect to étale hypercoverings. But you need a notion of homotopy hypercovering. So every time you do so think about a check cover, every time you do a fiber product, you replace it by the derived fiber product. And then you get the notion of homotopy hypercoverings. And F is a stack if and only if it has descent with respect to this homotopy hypercovering. So this is the, if you want, the Schiff condition. So some properties. So there is a derived version of the Yoneda lemma. So where I send a simplicial commutative algebra A to the map from A to something, where map is the map in the model category sense or in the infinity category sense. And this is fully faithful. And derived stacks as mapping spaces. So spaces of maps or simplicial sets of maps between two derived stacks. And it has also internal homes. And homotopy limits, so a homotopy version of limits and colimits. And for example, the thing to keep in mind is the last formula there, which tells you how to compute the derived fiber product of affine derived schemes. So that what you get is the spectrum of the derived tensor product the rings, the simplicial commutative algebras or the CDGAs. So there is a truncation and inclusion adjunction that goes from usual infinity stacks to derived stacks. So there is a functor I that view a stack as a derived stack, and there is a truncation. So each time you have a derived stack, you can truncate it, and you get the usual stack. Usual, I mean infinity stacks in general. And I is fully faithful, so you can embed the theory of stacks into the theory of derived stacks without losing anything. And the truncation factor is essentially defined by this formula. So the truncation of an affine is just the usual spectrum of pi naught of A or H naught of A if you work over sampling characteristic 0. And these factors are adjoint, and the adjunction map is a closed immersion. So you can see the truncation as a closed substack of the derived stack. And the intuition that you should keep in mind for this kind of construction is that if you have a derived stack X, this is like an infinitesimal or formal thickening of the truncation. So it's more precisely, one can prove that, so it's like having a reduced scheme inside the scheme. Okay, so you kill nilpotents, but here nilpotents are not real nilpotents, actual nilpotents, they are cohomological nilpotents. And this intuition is actually a theorem that tells you that the small étale site of the derived stack and the truncation, they are equivalent. So topologically, you don't see much of a difference. So far I've defined what are stacks, but I not defined algebraic stacks. So I want to define what are geometric objects. So it is like I've defined sheaves, and I want to single out which sheaves are schemes. Okay. So I take a notion of smooth maps. Again, there is a lifting property that, and there is a theorem that tells you that the map of commutative algebra is smooth if and only if it's smooth on the truncation pi naught, and it's everywhere else is a pullback. And then we can define what is a geometric derived stack. So first, the derived atlas is just a map from disjoint union of affines to our stack, our derived stack, which is surjective on pi naught, and there is some representability condition that I will not specify. If this map is smooth, étale or Zariski, then we get derived version of Artin, Deligne-Mumford, or schemes. And the truncation factors, which goes from derived stacks T0 to stacks, preserves the geometric type of the stack. So if you take a Deligne-Mumford stack and you derive the Deligne-Mumford stack and you truncate it, you get the Deligne-Mumford stack. If you take a derived Artin stack, you get an Artin stack. And using atlases, you can, just as we do with usual one stacks, we can extend the notion of smooth, étale, flat maps between geometric derived stacks. So one important property is this, is that the inclusion of stacks, usual stacks, for example, if you view a scheme as a derived stacks, this inclusion is a factor that preserves homotopy colimits, but not homotopy limits, and not even internal derived stacks map, internal homes. So in particular, a consequence of this is that the derived tangent space and derived fiber products of a scheme schemes viewed as derived stacks, they are not the scheme theoretical tangent space of fiber products. But this is a good thing. It's not a bad thing. It's a good thing because, for example, we can have an interpretation of the cotangent complex, a geometric interpretation of the cotangent complex in the following sense. So if you have if you start, for example, with Y, which is a usual scheme, then you view it via the functor I as a derived stack. So you take I of Y, and you take the usual definition of tangent, so tangent stack. So R spec from, map from spec of k of epsilon to this guy, to I of y. And then you prove that this is the same thing as the derived spectrum of the symmetric algebra on the cotangent complex. No, this is true in general. So this is a remark. It's not it's not hard to prove, and actually prove that the Grothendieck-Illuzy cotangent complex was already part of, in some sense, of derived geometry, because if you remember, it used simplicial resolution and so on. So this is not surprising, but it's good because it gives it gives an answer. Well, one answer to a question by Grothendieck that asked what is the space. There exists space whose tangent space is given by this formula using the cotangent complex.
What happens if you truncate and divide fiber product?
The truncation of a fiber product preserves, so truncation preserves fiber products.
So this direct tangent space would be an infinite one.
Yes, yes, exactly. It's I that doesn't preserve fiber product. T0, the truncation does. But of course, if you truncate, you don't get this. You cannot get. So if you take T of y, you know, if y is a scheme, T of y is not related to the cotangent complex. It's just the tangent space or the tangent scheme. So now we'll define the quasi-coherent complexes on a derived stack, geometric stack. So for example, Artin. So what I do is now I have to leave what I said before, I can do it in using model categories. Okay? But now I cannot do this anymore because I have to take limits in the infinity category. So I'm forced to use infinity categories. So one way to define the derived category, so if you want DG category or infinity category of quasi-coherent sheaves on X is the following. So you take an Artin stack, you write as the colimit of all the affine mapping to it. And then you define LQCO of X to be the limit of LQCO of a DG mod, okay? Where lim is the limit in the infinity category of stable infinity categories, or Siegel categories if you want. And LQCO of ADG mod is just the infinity category obtained. So you just take ADG mod as a model category. There you have a notion of quasi-isomorphism there. Take cofibrant objects, and then you localize with respect to quasi-isomorphism. So this is the infinity category, LQCO ADG mod. And not that if X is a scheme, you have this infinity category LQCO, and you invert weak equivalences, and then you get the usual derived category, triangulated derived category of quasi-coherent sheaves on X. So something I already said is that geometric derived stacks, they always have the cotangent complex, and the fact that we work in derived algebraic geometry makes this. This is essentially this theorem here, the geometric interpretation of a cotangent complex. This is true for any y, not necessarily a derived scheme. Scheme. And so it has a universal property. So in the case of for schemes, only some truncation of the cotangent complex has a universal property. And this is why it's hard to compute sometimes the cotangent complex in algebraic geometry. So here there is a full universal property, so it's computable. You can compute. And for example, you can give it I don't have time to do that, but you can give you can explain in some sense all the tricks that you do in the formation theory using. There are no more tricks in this. Okay, this is a bit. Anyway, we can talk about it later. Anyway, you can really explain what is for example, obstructions becomes deformation over some derived rings. So you can really have functoriality of obstructions in a complete in the same setting. So you don't have to do nothing strange. It's completely natural here. So one other feature is that the base change formula for quasi-coherent sheaves holds even without flatness assumption. Of course, you need some hypothesis. For example, that this diagram there is its Cartesian diagram is made of quasi-compact derived schemes, but you have this base change formula even for in non-flat cases, which is of course a very good thing to have. And another thing I want to mention is that you can, if you take the derived internal hom, so between two derived stacks, so x and y are derived Artin stacks, and you take the mapping derived stacks between them. If this is a derived Artin stack, so there are conditions which is true, and I wrote some condition there, but there are other possibilities. If this map is again an derived Artin stack, then the tangent is given by what people use to make deformation theory for maps. So hypercohomology of X with value in the pullback of the tangent complex. And there is a global version written in the formula T map is the PR lower star evaluation upper star of T of Y is the global version of this. And this is completely false in algebraic geometry in general. But this is, again, this is something that if you want to do deformation theory for maps, a scheme of maps, you use this deformation complex. But in that case, it's not the tangent of anything. Yes. Flat, I think it's OK. I think flat is OK. It's enough. OK, now I want to define, I want to go towards symplectic forms and Poisson bivectors. So I want to define first what are P forms and closed P forms on these objects derived Artin stacks. So let me start with the affine case. So I start with now we are in characteristic 0, so I take my models for affine derived schemes are just CDGAs. Then I take a cofibrant replacement of a CDGA A. And then I take the sum of the cotangent complex. So the wedge of the wedges, P wedges of the cotangent complex, which is the same thing as I take a cofibrant replacement, the usual Kähler differential of A prime over K. This is a bicomplex with two differentials. One differential is induced by A prime, and one differential is given by the RAM differential. I take the naive Hodge filtration FQ, where I sum over all the P bigger than Q, and this is still a B complex. And then I define the complex of closed P forms to be the totalization with respect to product of this Hodge filtration at P shifted by P. And if I want to define n shifted closed P forms, I just shift the definition above by n. That's easy. And you also have, if you unravel the definition, you also have an Hodge tower, which is written there. And you can compute the homotopy fibers of this Hodge tower. And the homotopy fibers are given by forms, not closed forms. So I will come back to this in a minute. So the complex on the right there, A0 closed of A, is just Illusi derived RAM complex. There is an underlying P4 map that goes from closed P forms with the shift n to the wedge P of the cotangent complex shifted by n. But this map is not an inclusion. Okay, so this means that saying that a form is closed is not a property. It's a set of coherence data, okay? Because there is an homotopy fiber which in general is not contractible, even contractible. So being closed is not a property, but a list of data. So another point of view on this, which is the one that we currently use, is the following. Maybe I will refer to this later, so let me go briefly through it. So we can define these closed P-forms and P-forms in a different way. So we start with the category of graded mixed CDGAs, so which is what you expect. So it's a bunch of BP together with a mixed differential, which I call epsilon, which goes from the part in weight P to the part of weight P plus 1, and you shift by 1, and it's squared to 0. This is the mixed differential. And there is a product map. So BP, so the part in weight P times the part in weight Q goes into the part of P in weight P plus Q, and it's associative, commutative, and compatible with the mixed differential. There is a functor from these mixed graded CDGAs to just CDGAs that only takes the 0 part, and this functor has a left adjoint, which we call the Derived algebra, because actually, if you forget the mixed differential, is just the symmetric algebra on the cotangent complex shifted by -1. So it's underlying CDGA is really the Derived algebra. And then you can define in an equivalent way, closed P-forms as a map from in the model category of DG model graded and mixed from KP with this strange shift. So KP means means K in weight P, and minus P minus N is the shift, the usual homological shift, to this Derived algebra. While closed forms, you take the K in degree N, and you map it to the wedge of the cotangent complex. And from this definition, you see that there is an induced map, and this is the underlying P4 map that we saw in the previous slides. Then we can glue this. This was defined for affine. Then we want to say what are P-forms and closed P-forms, eventually with some shift on the derived Artin stack. And so what we do is that we take these functors. So to any A, we associate so AP of A with a shift, or we can take the closed version. And these are the nice thing is that because the cotangent complex of an étal, so the relative cotangent complex of an étal map is trivial, these are actually derived stacks for the étal topology. So you get a map of stacks from closed P-forms with a shift N to non necessarily closed P-form with a shift N. And then we can define what are P-forms and closed P-forms on derived Artin stacks. So we just take these AP closed and APN as classifying stack for P-forms and closed P-forms. So we map. So AP of X will be mapped from X to AP, and AP closed of X will be mapped from X to AP closed. Okay, these are spaces of P-forms and closed P-forms. When I take an element in pi naught, I say that I have a P-form or a closed P-form. Let me also mention that if X is a smooth scheme, there are no negatively shift forms, so that exist. So pi 0, when n is negative, is empty. While in the opposite case, when you start with, for example, an affine derived scheme, there are no positively shifted forms. This is because of the amplitude of the cotangent complex. But for general X, you can have shifted p-forms and closed p-forms of any shift, of any integer shift. So again, we have an underlying p-form map for a derived stack. Again, this is not a monomorphism, but the homotopy fiber is quite complicated in general, and we call it the space of keys because it's the space of data that you need to close the underlying form. If X is a smooth and proper scheme, then indeed this homotopy fiber is contractible, and essentially so this underlying P4 map it's a monomorphism. So nothing new in the smooth and proper scheme case. Okay, skip this. Then we can define what are symplectic form and shifted symplectic forms. So take an Artin stack whose cotangent complex is perfect. Then I say that what is the space simple xn of n-shifted symplectic form of X? I take the space of closed forms. I map it to the underlying A2 of xn. And I take the one which are non-degenerate. Okay? Then I take the connected components of this. This gives me a space, and this is the space of symplectic n-shifted symplectic structures. Where non-degenerate means simply the thing that you imagine. If the underlying two form is a map from OX to LX wedge LX shifted by n, then you take the adjoint and you require that the adjoint from TX to LX shifted by n, it's a quasi-isomorphism, or an equivalence in NQ code. Okay, so this is nothing special. One thing I would like to mention is that this non-degeneracy here, condition that Tx to Lx shifted by n is an equivalence in the derived category, is an isomorphism in the derived category. It mixes the stacky degrees with the derived degrees, okay? Because in general n can be negative or positive. So, and it's quite a tricky. It's quite a tricky condition. And one other thing I would like to give, first, there is an easy example for G equal to GLN of the case when the stack BGLN has a canonical two-shifted symplectic structure. Okay. And this is given by the formula that I wrote there. You just fix, well, here you don't have anything to fix. You just take the map that goes from a pair of matrices to the trace of the product. This is GLN invariant, and it's non-degenerate, and it gives you, if you unravel the definition, it gives you exactly the underlying two form of something that you have to prove that it's closed. But this can be done. And you can extend this to reductive, to any reductive G. Another example of something which is symplectic is you just take the shifted cotangent of any derived Artin stack. The shifted cotangent is the spectrum of the symmetric algebra of the tangent complex shifted by minus n. Okay, so if the shift n is 0, this is just the cotangent stack. And you can prove that you always have T star x n shifted as an n shifted symplectic form. Group cohomology? Well, stacky means, okay, if you look at CDGAs, stacky is the part in positive degrees, and the derived part is the part in negative degrees. Yeah, yeah. Yes, exactly. Yes, exactly. Okay, those were examples of easy examples of derived Artin stacks that have some symplectic, shifted symplectic structures. But let me give three more general existence results. So the first thing, the first example is in this, the first theorem is in these slides. It's an analog of what is called the KSG theorem in the physics literature. So let me state it like this. I mean, it's stated in full generality there, but let me say that you consider the derived mapping stack from X, where X can be a Calabi-Yau of dimension D, or a topological, compact topological oriented space of dimension D. Okay. Then you take map from these, any topological space gives you a derived stack, because any topological space gives you a usual stack. So, okay, so you can consider map from this oriented guy, so Calabi-Yau of dimension D, or compact topological oriented dimension D, to something which is already, which you know it's already n-shifted symplectic. Then the mapping stack is n minus d shifted symplectic. So there is a canonical induced symplectic, n minus d symplectic structures. This will be important in Donaldson-Thomas theorem, and if I get to that. And in general, this is the way I stated here, but there is stated in full generality. And basically, orientation is something that in algebraic geometry refers to Grothendieck Serre duality, and in the topological case, to Poincaré duality. But there is a common framework for both of them. And so we can prove the theorem in one step and not specializing to each case. Now the second existent theorem is for Lagrangian, for intersection of Lagrangian. So let me tell you what is roughly speaking, what is a Lagrangian structure. So you have a map from X to Y, where Y is already n-shifted symplectic. And the map is not supposed to be closed immersion, I mean, it's anything. Then you say that this Lagrangian structure on this map is a path in the space of closed two forms, from the pullback of the symplectic form to 0. So you would like to say that it's 0 on the nose, but this is not good homotopically speaking. So you say that there is a path that witness the 0, the fact that f upper star of omega is 0, and it's non-degenerate in a suitable sense. This path gamma. For example, if you have smooth Lagrangian in a usual symplectic, smooth symplectic scheme, then they have essentially a unique Lagrangian structure. It means this what I wrote there, that that if you take, there is an induced map. If you unravel, play a bit with the transitivity sequence, you get a map from the relative tangent complex T of f to the cotangent complex of the source shifted by n minus 1, and you ask if this is an equivalence. If you are in the usual case, this tells you that the dimension is half the dimension. Okay. This is equivalent to tell of course there is no dimension here, but in the smooth case for schemes, this tells you exactly the same. And one interesting observation is that there is a bijection between Lagrangian structure on the canonical map from X to spec K, where you endow spec K with the spec K can have any symplectic structure of any degree. You take degree n plus 1, and you giving a Lagrangian structure on this map, which is canonical. It's the same thing as giving an n-shifted symplectic structure on the source X. So Lagrangian structure in this context are generalization of symplectic structures. And the theorem is the following. So if you have two Lagrangian two maps from L1 and L2 to F, F is symplectic, and you have two Lagrangian structures on these two maps, then the homotopy fiber product of these two derived stacks, it's n minus 1 shifted symplectic. So if you take the two Lagrangian, I mean the intersection on something which is n symplectic, the intersection lose 1 degree of shift, but it's still symplectic. This applies in particular to the case where everything is smooth. So there is this funny thing that if you have two Lagrangian in a usual smooth symplectic guy, the intersection you cannot say too much. But the derived intersection is a -1 shifted symplectic. So let me give just a sketch of the proof very quickly. In the usual case, so everything is smooth, non-derived, everything is classical. So so I have L1 and L2 inside M. M is symplectic. Then I take the derived intersection, not the intersection. And then, since this is a derived fiber product, there is a canonical homotopy from the pullbacks, the two pullbacks of omega to L1 and L2. Okay? This is by definition, if you want, of derived fiber product. But L1 and L2 are Lagrangian, so this path, this canonical homotopy, gives you actually a loop at 0 because they are Lagrangian. Okay? So you compose with the path that you had before, and you get the loop at 0. So let's see what is the self-homotopy of the 0 form. It is a map from the wedge 2 of the tangent of the intersection to structure sheaf of the intersection shifted by -1. And it's a map of complexes because it's a self-homotopy of the 0 form. So you have dH minus HD equal to 0 minus 0, which is 0. So this tells you that it's a map of complexes. So H is a -1 shifted 2 form. And then you have to prove that it's come from a closed 2 form, but this can be done. Okay, so this is vaguely the idea. Last existent theorem I wanted to mention is the derived symplectic structure on the stack of perfect complexes. So the stack R-perf is the stack that classify perfect complexes on CDGAs. It's a derived stack, and it's if you don't fix the cohomology amplitude, I mean it's not of finite type. It's not locally. It's only locally arting. Okay, but if you fix, it's arting. And the statement is that this stack the R-perf of perfect complex is 2 shifted symplectic. So in particular, the corollary is the following. If you apply the two theorems on map and this theorem on perf, and you take map from X, which is a Calabi-Yau of dimension D, to R-perf, you get simply the stack of perfect complexes on the Calabi-Yau. And this stack is 2 minus 2. There is a 2 minus D shifted symplectic structure. The corollary on dimension 3 of this theorem and the theorem before is that you have if D is equal to 3, then you get a -1 shifted symplectic form. And if you see what it means, it gives you what is called a symmetric obstruction theory by Berendt and Fantecchi. And actually you can prove, but the fact that it's, so the definition of Berendt-Fantecchi symmetric obstruction theory is essentially the underlying form of this shifted form. The fact that it's closed tells you more, and in particular allows you to prove this long-standing conjecture that there exists a Donaldson-Thomas potential. This was proved by Brav, Bussi, Dupont, and Joyce in 2013. So locally, the Donaldson-Thomas moduli space is the critical locus, locally Zariski. So that's very strong condition. Locally Zariski, it's a derived critical locus of some function, but on a finite dimensional smooth scheme. So no gauge theory. I mean, this was already known, but for infinite dimensional spaces. But this is it's a very finite dimensional model. And let me also say that all known examples of symmetric obstruction theories in the sense of Berendt and Fantecchi actually come. So they have more structure than what's in that definition. They are -1 shifted symplectic structure. So let me go to derived Poisson structure. So for the moment, I will concentrate on derive the Lee-Mumford. For Artin, it's more complicated, and maybe I will say a few words later. So what is the space of n-shifted Poisson structure? So you take the space of DG Lie, graded DG Lie maps from k minus 1 in weight 2. So k is in cohomological degree 1, and it's in weight 2. The gr in the grading is the weight grading. And you map it to essentially polyvectors, shifted polyvectors, okay? R gamma of x sim tx, etc. These are shifted, version of shifted polyvectors. Here, the Lee-Mumford, so there is an étal atlas and there is no product. There is a shifted version of the Schouten-Nihenhuis bracket here, and this is a DG Lie. And you take maps from this to this, what it means. Since you are mapping from K, you take the image of 1, this is what? It's something in some degree, but it's in weight 2, so it's a 2 vector. It's a polyvector of degree 2. And the fact that K on the source, it says trivial bracket, tells you that essentially that the bracket of the image of the generator with itself is 0. So it tells you that it's a Poisson structure. So this is why we use this definition. But this is a definition which is homotopy invariant. But there is also another notion of Poisson structure on X for X derived affine, so where X is a R spec of A, where A is a CTGA. And it's just the notion of PM algebra, okay, where PM is the Poisson operand, shifted Poisson operand. Okay, there are these two notions which are a priori different, but actually they are true. I mean, this was proved by student Valerio Melani last year, that the space of Poisson structure on a derived affine with the shift n is well, it maps to the space of Poisson n plus 1 structure on A as a CDGA, and this is a weak equivalence if the cotangent complex is perfect. Okay. Let me go to derived coisotropic structures, which is something under investigation. So let me give a definition of derived coisotropic structure. So if you have a map of CDGAs from A to B, then you have these, you can consider polyvectors with some shifts. So pol A n plus 1 with a shift n plus 1. And it maps, using the map F, to the polyvector, the relative polyvectors, but shifted by, well, the shift is n. So the shift outside is n plus 1 for both, but the shift inside is n because you are using the transitivity sequence. So you lose one shift. There is this map. You take, this is a map of DG modules over K. You take the homotopy kernel of this, and you prove, I mean, Valerio Melani proved that this homotopy kernel has a natural structure of L infinity algebras, L infinity algebra, such that if you shift back the relative polyvectors, you get an extension of DG Lie, so a fiber sequence of DG Lie. A fiber sequence, I mean, in the homotopy category of DG Lie. So the homotopy category of DG Lie is the same as L infinity algebras. So this is why the things are related. Then a derived coisotropic structure. So if you remember what is, so you have a map from A to B. Then pi, if pi is by definition is a Poisson structure and then shifted Poisson structure on A coisotropic structure is a lift of this pi to a map from K minus 1 in weight 2 to this LF, which is L infinity algebra we defined before. And the space of lifts is the space of coisotropic structure on the map F. So this definition can be extended to derive the Riemann-Mumford stacks, but for Artin stacks you need something different, so another definition. And for usual, so zero shifted Poisson structure on smooth scheme, you can prove, though it's not completely obvious, you can prove that this definition is exactly the same as the usual definition of coisotropic structure on subvarieties of smooth subvarieties. And again, you get a result like the one I mentioned for symplectic. So the space of Poisson n-shifted Poisson structure on X is the same thing as the space of coisotropic structure on the map, canonical map from X to spec K, where you endow spec K with this, with the unique n+1 shifted Poisson structure. So again, coisotropic is a generalization of Poisson in this context. So let me mention this result, which is almost written down by Valerio Melani. If you take, so they are analogs of what we got for the symplectic case for intersectional Lagrangians. Okay? Here we are in the Poisson case, and you replace Lagrangian by coisotropic, and then you get this result. But they are harder to prove. So let X be an n-shifted Poisson, and then you have two maps to X endowed with a coisotropic structure. Then the derived pullback is canonically n-1 shifted Poisson. And you have an analog theorem for mapping spaces. So if you map something which is D-oriented, for example, a Calabi-Yau of dimension D, or a topological space compact of dimension D, to something which is n-shifted Poisson, then you get an n-d shifted Poisson structure on the mapping stack. And since you can prove, though it took us a lot of time, since you can prove that n-shifted symplectic is the same thing as non-degenerate n-shifted Poisson, then this theorem is a generalization of the theorems that I stated in the symplectic case. Though this result, n-shifted symplectic, is equal to non-degenerate n-shifted Poisson, it's funny to say, but because it's two lines in the classical case, but here it's not that easy, at least in the Artin case. But it's true. So I think I will only have time to finish with some words on quantization. So let me define in the general case of the derived Artin stack what are symplectic and Poisson structure. So if you start with the derived Artin stacks, you have this what is sometimes called the Grothendieck-Gelfand connection. So you map X to X deram. X deram is the stack that is associated to A, to a CDJ A, the value of X on the reduced part. So take H naught, and you take the reduced part of that. And if you take the X to X deram, you take the fiber over say, a K point of this. The fiber is the formal completion of X at little x, or at the point. So you can view this family X to X deram as a family of formal completions of X at points of X, because this is what it is. Then you can define what I call ADR of X, which is a sheaf of OX deram linear mixed graded CDGAs on X deram. And the property is that the value on spec B is just the derived algebra, sorry, the RAM algebra that I defined before, relative, so B reduced relative to B. And out of this thing, you can recover the P forms on X, closed P forms, symplectic forms, just using this sheaf of OX DRM linear mixed graded CDGAs. And you can recover Poisson, the shifted Poisson structure, the definition I gave for Deligne-Mumford, and you can use it to define Poisson structure in the general Artin case. The problem with polyvectors is that polyvectors, they don't have, if you are outside the étale topology, the étale atlas, they don't have any functoriality. So there is no hope to extend to the derived Artin stack, the definition I gave before. But you can give a general definition using this A theorem of X and prove that in the Deligne-Mumford case it's the same, and so you get also definition for derived Artin. And now what we gain is that both symplectic and Poisson structure are defined on the same objects. Using the same object, this is sheaf A theorem of X. So they are easier to compare, and in fact, the canonical map from non-degenerate Poisson to symplectic, you can prove it that it's an equivalence of spaces. But even having this map before using this common language, it's I mean, we were not able to do that. And you can also say what are perfect complexes on X using this A Deram of X. There is an explicit subcategory of A Deram X mixed DG modules that are equivalent to perfect complexes on X. Okay, this is essentially. Then, in the last 3 minutes, I want to say something about quantization of derived modular spaces. So what is the idea? So we start with X is, say, derived Artin stack with a perfect cotangent complex, and we want to deform the DG category or the infinity category of perfect complexes on X. So this is the rough idea, which is very easy written this way. But anyway, it's not so difficult to formalize it. So suppose that I have on X an n-shifted Poisson structure. Then, by definition of Poisson structure, the new definition I have tells you that A Deram of X, so the sheaf of OX Deram linear mixed CDJs, is a Pn+1 algebra in the sense of in the operatic sense. So in particular, it has a bracket, and I can deform the bracket over A1 by multiplying by T, so the stupidest thing to do. So I have a family of Pn+1 algebras over A1. Okay? And then I apply formality here. So I choose an associator and apply formality to change this Pn algebra to an En+1 algebra. So I get an A1 family of an n+1 algebra structure that deform the algebra A Deram of X. But then I know that a subcategory of mixed DG modules over A Deram is equivalent to perfect complexes on X. So we get a deformation a family of deformation of this DG category of perfect complexes on X. And it's a deformation, if you unravel the definition, of this DG category as En monoidal DG category. So it's, in the world of DG category, infinity category, you have E0, which is no tensor structure, E1, which is just associative, E2, which is braided, and then you get E3, E4, and so on. They are all different. There is no Ekman-Hilton argument that works. So they are all a higher approximation of E infinity, which is what you may think about being commutative. And since L perf, it has a tensor product and it's symmetric, so it's E infinity, so it's En for any n, and you can ask for deformation for any n. And this is what you get if you have a shifted Poisson structure. And when X is nice, so it's this LQ-co is compactly generated, then you can get an induced quantization on the whole category of the DG category of quasicoherent complexes. Well, this works for n bigger than 0. It also works for n for negative n, but you have to change the parameter space. It's something that has a twist because, of course, for example, E minus 2 doesn't make sense. Okay, so E minus 2 doesn't make sense. But if you change the degree of the parameter, you still get a formal deformation of E2 in this case, or E absolute values of n. And recall that we have used an associator there because we have used formality. So there is an action of the Grothendieck-Teichmüller groups on the modular spaces of all quantization. What is expected is when the structure is symplectic and not only, so it's Poisson non-degenerate, then this action, so it's essentially trivial in the sense that there is only one quantization. While in the general Poisson case, we expect that there is a modular space of quantization. And so this is for n positive, for n negative. For n equal to 0, we don't get a family over A1, but just a formal deformation. for x, which is as complicated as the derived dilemma for stack. But for example, the case n equal to 0, and x artin is completely out of reach for the moment. And let me recall that the case, the smooth case, n equal to 0 is Kontsevich theorem. Okay, so I'm out of time, so let me just finish with this slide. But there is a list of quantizable derived modular spaces, which is good to finish with. So all these derived modular spaces are admit a quantization. Especially the last example is interesting because maybe it's related to what Daniel will be talking about later. Okay, thank you very much. Sorry for that.